Welcome everyone to this webinar. We will present today some results from the HIVAX project. So this project is about HIVAX, means high voltage aerospace cable system. So my name is Laurent Albert. I'm working at IRT Saint-Exupéry, and for this webinar, this webinar will be also presented by Thomas Hanner from Nexans, Ian Cotton from the University of Manchester, Gilbert Tessad from the University of Toulouse, and Robert Londes from the University of Manchester. So I will just a quick introduction about a quick overview of the project. So on the context, we all know that we have to reduce our emission. So it's here, and so for the aerospace industry. I'm sorry, people could mute their microphone, please? To do that, one way could be to use more electrification in the aircraft by, for example, using new propulsion techniques architecture like hybrid aircraft or electric aircraft. And this will lead to an increase of the electrical power. And this increase will lead to higher voltages and currents. So there are needs to develop new electrical wiring systems used to transfer the power across the aircraft. And that must be reliable, compact, and as light as possible. So the HIVAX projects have two main objectives. The first one is to bring a package of models. We need these models to design the cable. So we need some electrostatic model, thermal model, edging models. So one goal is to bring this package of models, but also to have a clear experimental validation of these models. And the second objective of the project is to explore the design and do some optimization to design the future aerospace cable system. As you can see at the bottom of the slide, this project is a European project, so part of the program Horizon 2020, and more precisely Sky Journey program. You can see the topic addressed by this project. For this project, the topic manager is Rolls-Royce. And about the budget, we are a little bit less than 1 million euro, and for the duration, a little bit more than 2 years. But as you can see, we are now on the finishing line because we finished this project this month. Just quick, the member of the consortium. So the consortium include 4 members. One an industrial member, which is Nexans, so a well-known cable manufacturer. And after that, the 2 universities, the University of Manchester and the University Paul Sabatier Toulouse, specifically the Laplace Laboratory. And the last one, I will just take quickly 1 minute to explain, because we are not well known. Institut de Recherche and Technologie Antoine de Saint-Exupéry, also known as IRT Saint-Exupéry. So we are a French private research institute and a non-profit organization. Our main locations are in Toulouse and Bordeaux in France. And our research are supported by the French government and our industrial members, coming mainly from the aerospace industry. We cover a large topic of technical topics. For example, we work on voltage increase in the aircraft, wide bandgap electrical component application. We work also on high performance materials, artificial intelligence, and many more. So if you want to know better, you can visit the IRT website and you will learn more on this institute. So here is the agenda of the webinar today. So 6 presentations. The first one will be done by Thomas about challenges in cable design and manufacturing. Then Ian will speak about thermal modelization to design the curing capacity of the cable. I will then present what we have done at IRT on the experimental part for the thermal validation. Then Gilbert will talk about aging mechanism and some concern on aging. And after that, Robert will explain some concerns, some difficulties about partial discharge testing and how it's difficult to deliver consistent PDIV results. And finally, Robert and Ian will present some design exploration and optimization. So about the question part, I kindly ask you to write your question directly in the chat box whenever you want. Speaker or consortium members will answer them interactively. So we can start now with the first technical presentation. So Thomas, you can go on.
Okay, thank you, Laurent, for the introduction. I start to share my screen.
I start to.
So do you already see my screen there? Hopefully. Yes. Do you see my presentation?
Yes.
Yes, thank you.
It's good now.
Okay, good. So I'm Thomas Hähne from Nexans, one of the leading cable manufacturers in general, and in particular for aerospace cables. I'm the technical manager, and I'm based in our lead factory in Draveil, which is located close to Paris. And I'll give you an overview of the challenges in the cable design and manufacturing related to high voltage cables. So here we have a summary of the different constraints we have to take into account for the cable design, like the environmental constraints related to the temperature range of -65 to 260 degrees C, flammability, resistance to humidity, fluid, sulfur, fungus, and the low pressure due to the high flight altitude. In addition to that, we have installation constraints related to the requirement for low bending radii and the resistance to scrape abrasion, notch propagation, and cut through. And then, of course, we have some additional constraints related to the high power, high voltage, high current needs for hybrid electrical aircraft. And here we also have to take into account the waveform. Shall it be DC, sinusoidal AC, or switch DC, also known as PWM? And of course, the frequency. We have to consider electromagnetic interference between the different systems. Short circuit currents have to be taken into account, and we are targeting a partial discharge-free operation in the operating voltage range. Regarding partial discharge, we have different sources for partial discharge. So partial discharge could appear in the air gap between wires, or between wire and ground, or in voids inside the insulation. To avoid the partial discharge in the air gap between the wire and ground, we may use screen cables, as those contain the electrical field inside the insulation, and hence partial discharge may only occur in voids inside the insulation. Screen cables in the context of high voltage cables means it's not related to an EMI screen, but it means that we have a 3-layer insulation system where we have a first semiconductive layer on the conductor screen, and then a second semiconductive layer on the insulation screen. And those semiconductive layers, they contain the electrical field inside the bulk insulation. If we do not use screen cables, we will need relatively thick insulation for the unscreened cables. So here we see estimated insulation thicknesses in millimeters for a given or for a required partial discharge inception voltage. So we see that the higher the voltage, the thicker the insulation has to be. And of course, the higher the altitude or the lower the ambient pressure, the thicker the insulation needs to be. So if we focus here on, for example, on the 2 kilovolt PDIV, then we would need an insulation thickness of roughly 4 millimeters. The advantage of using a screened cable is that for one and the same insulation thickness, we can operate the cable in a large voltage range as long as the operating voltage stays below the breakdown voltage of the insulation. Typical breakdown field strength for PTFE or PFA insulation is 15 kV per millimeter. So for 1 millimeter thickness, insulation thickness, we could work up to the several kilovolt range. And of course, as the electric field is contained inside the insulation, we are pressure independent, provided that the insulation has only little small voids or no voids at all inside the insulation. The estimation of the partial discharge inception voltage is based on the Helix method, which in principle is for uniform fields, but we measured it also, or compared the prediction with measurements on cable samples. So the blue line is the partial discharge inception voltage in function of the pressure for thickness, insulation thickness of 0.5 millimeter, and the green line for thickness of 1 millimeter. And the dots are here the measurements we did, and the measurements showing also the 3 sigma error bars. So from that graph, we can say that the method we have used to predict is in good concordance with measurements. In a first step, we tested different model cables using a conductor size of gauge 12. So we have been using 5 different designs. The first 2 one using a PTFE tape wrap insulation, one with what we call a standard wrap and one with a fitted wrap. The fitted wrap is supposed to generate less voids at the overlap of the tape. And a third one using a PFA, so extruded PFA insulation. All the 3 have the same thickness of 0.4 millimeter. And then we have thicker PFA extruded insulation of 1.7 millimeter or 1.8 millimeter. And then the 5th one is a screen cable with semiconductive layers on the conductor and in the insulation. Here on the right-hand side, we see the results of the partial discharge inception voltage in volt root mean square, measured at normal temperature at pressure. And for the 3 cables having the same thickness of 0.4 millimeter, we obtain roughly the same partial discharge inception voltage. Then when we increase the thickness from 0.4 millimeter to 1.8 millimeter, we increase also the partial discharge inception voltage. And you may also note that there's no linear relation between the thickness and the partial discharge inception voltage, because here we have increased the thickness roughly by a factor of 4. But the voltage is only increased roughly by a factor of 2. And then we have the 5th cable where we have added the semiconductive layers. And here the partial discharge inception voltage is above the limit of our generator. So it's above 10 kV. So we don't know what is the actual value. We can only say that it is above 10 kV. The results we have shown here have been obtained on 10 samples, where each sample has been measured 10 times. So it's 100 measurements here. You will see later on a presentation dealing with the with a round robin testing, where we compared the results of different laboratories and different test configurations. In the next step, we also tested bigger size cables using a gauge 0 conductor. And here we have two screen cables, the number 1 and the number 4, where we have been using conductive PTFE tapes as conductor screen and insulation screen. And the design number 2 and 3 is, let's say, a standard design using an insulation with a PE tape on the conductor and PTFE tapes on above that. And we made, of course, different thicknesses, so 0.25 and 0.5 millimeter. Here on the right hand, we see the obtained PDIV results, and surprisingly, the PDIV of the screen cables is quite low, much lower than what we have expected. So, for example, for the first one with the polyimide tape as insulation, we only have 1 kV of PDIV, and for the fourth cable with the thick PTFE insulation, we only have 3 kV. And for the two cables, the two unscreened cables, again, we see the increase of the PDIV with insulation thickness. And again, we see that it is not a linear relation. So how do we explain that the PDIV is so low for the screen cables? It is related to the fact that we have voids in the polyimide layer insulation, but also in the PTFE layer insulation. So, for example, here we see a big void in the polyimide layer, which is also seen here in the design number 3. So those voids are created during the sintering of the PTFE insulation, which is above the polyimide. During the sintering of the PTFE, it shrinks in volume by 25% roughly. So we have, whereas the polyimide doesn't change. So we have then some radial forces on the polyimide, which then creates those buckles and voids inside the PE insulation. In addition to the voids in the polyimide insulation, we also have the voids in the PTFE insulation at the overlap of the different tapes. And here for the thick cable with 2.7 millimeter insulation thickness, we have a lot of overlaps and hence a lot of voids inside the insulation. So our conclusion is that the tape wrapping process is not a suitable process for high voltage cables, and that we should better use insulation which is applied by melt extrusion process. There are only few materials which can be used for that, which have the required properties or properties which are close to what we use today, to the PTFE insulation. So the best candidate we had found is PFA, because it has also a wide operating temperature range. It has a low dielectric permittivity, low dielectric losses, low conductivity, and also has a high dielectric breakdown strength. So at plates of 0.5 millimeter thickness, we have measured a breakdown strength of 60 kV per millimeter. The slides here show some electrical properties of the PFA we have obtained. So those are measurements in the frequency range up to 1 megahertz at different temperatures. And the measurements are done at low voltage, at 1 volt. And here we see that the dielectric permittivity doesn't change with frequency, but it changes with the temperature. It decreases with increasing temperature. And on the other hand, the dielectric loss factor, the tangent delta, is quite low, in the order of 10 to -4, which means that we can neglect dielectric cable heating due to dielectric losses. On this slide here, we see again the dielectric permittivity and the dielectric loss factor, but now measured at different voltages or electric field stresses, up to a frequency range of 10 kV. And again, here we see that in the range up to 2 kV per millimeter, there's only little variation of the dielectric permittivity and the dielectric loss factor. Regarding the semiconductive layer, we have been using a semiconductive PFA, because then it has the same base material than the insulation PFA, so having the same thermal properties. So we avoid then a delamination of the 3 layers during thermal cycling. And also the semiconductive layers shall be bonded tightly together to avoid any delamination. The semiconductive layer shall be sufficiently conductive to contain the electrical field inside the insulation. For land high voltage cables, typical value for the volume resistivity is in the order of 500 ohm meter. The one we have been using, the semiconductive PFA, we have obtained a conductivity of, or a volume resistivity of 50 ohm meter. Additional aging results for the PFA will be shown later in the presentation from Gilbert. As said before, the 3 layers shall be bonded tightly together. That can be achieved by an extrusion process where the 3 layers are applied simultaneously in a co-extrusion process. So here we see the extrusion line with the main extruder here in the middle for the insulation, and on the left, on the right, the extruders for the insulation screen and the conductor screen. So those 3 extruders, they are connected to the crosshead, the extrusion crosshead. So here we have from the right hand the conductor, which goes inside the extruder, and then here on the left hand, that's the exit of the crosshead. We have the insulated wire with the 3 layers, so conductor screen, insulation, and insulation screen. As those 3 layers are tightly bonded together, you can't peel them off from the insulation like a banana skin. So you need some specific tools. So here we have a specific tool which is suitable for a wide range of diameters. The disadvantage of that is that the setup of the tool takes some time, because you have to adjust it to the diameter of the cable, which is shown here in that short video. And so here you fix the tool on the cable. Then you adjust the blade. And once you have adjusted it to the cable diameter, then you have to adjust the deepness of the blade for the shaving. On the other side, you see a tool which is suitable just for one and the same cable diameter. Of course, in that case, the setup is quite quick, and you can use it together with a with a drill. And you see here the video where the semiconductive layer is stripped off. And here you go. And there on the left-hand side, you see how the semiconductive layer is peeled off on that with the manual system. Then for the HiVax project, in addition to all those model cables, gauge 12 and gauge 0, we have also manufactured, designed 3 cables and manufactured them. So there is a screen cable, the design number 1 with the semiconductive layer, an unscreened cable but shielded, so it still has an EMI braid around the insulation, and a third one without any screen or EMI braid. So those cables had been designed for DC bus voltage of 3000 volts and for PDIV partial discharge inception voltage, face to ground of 4500 volt peak and face to face of 9000 volt peak at a pressure of 238 hectopascals or 35 kFeet. So here you see the design details and the cross-sectional cut of the cables we have manufactured. It is interesting to note that all cables have roughly the same diameter, outer diameter and cable mass, whereas the design number 3 doesn't have any EMI braid, of course, so there's some additional mass to be added once you have built up a 3-phase cable. And what is also interesting is that when you have a screen cable or a shielded cable, at least a shielded cable, the face-to-face voltage is converted to a face-to-ground voltage. That is to say that from the cable perspective, you have to consider only the face-to-ground voltage, whereas for the unshielded, unscreened cable, the limiting factor is the face-to-face voltage. That's why for the unshielded, unscreened or unscreened, unshielded cable, the thickness is thicker, 3.2 millimeters compared to the 2 millimeters. In the following presentations, you will see simulation results on the current carrying capacity of such cables and so on. So you will get further details which explain why those cables have been chosen in the other presentations. I think there have been a lot of questions right now because I hear my phone. Okay, I'll just leave the presentation so to be able to see the chat. Where's the chat? Okay. I start with the first one, hopefully. Oops. So the question, in the case of screen cables, is there any implication? In the case of screen cable, is there any implication on ground system that can be used? I'm not sure to understand the question.
So I think, Thomas, I think some of these we've tried to answer as we go in chat, but you know, if other colleagues have got ideas about views on these. There was one question probably a bit further down which Patrick has given a quick reply to, but I wonder if you want to pick up. There was one from Chris Evans from the Boeing company on just about, you know, can you do something different with tapered edge tapes in manufacturing?
Tapered edge tape, you mean some smooth tapes which in principle should avoid voids inside the insulation. Yes, that may be a solution. However, the problem is if we need a thick insulation, let's say 1 millimeter, for example, it is not reasonable to apply 1 millimeter thick insulation using tape wrap. I think in one of the slides I've shown that for 0.5 millimeter PTFE tape insulation, for 0.5 millimeter thick insulation, you need 5 tapes. So if we go to 1 millimeter, it would mean that we need 10 tapes. So 10 tapes, they can't be applied in one and the same process. So you have to have, let's say, 4 taping steps. So the more taping steps you have, the more the risk to include foreign particles inside the insulation. And then again, if we still have the polyamide tape underneath the PTFE insulation, then we still have the risk of creating voids inside the PE layer. But in principle, yes, the idea of using smooth tape or tapered edge tape is a good idea to reduce voids inside the PTFE insulation.
And I think Thomas Boris Schwert from Airbus has asked about the triple point. You know, at the end of the screen. So I've quickly flagged absolutely it's an issue. You know, and you need suitable terminations. So I don't know if you want to add a manufacturing view about, you know, the need for terminations connectors suitable for the cable.
Yeah, I agree that you will need some field grading material. That you will need some field grading material to avoid partial discharge or surface discharge due to the triple point. The problem will be, or is, that today there are no field grading materials which are off the shelf, which are suitable for aircraft applications. So firstly, due to the high temperature range, then secondly, also due to the PWM voltage, which has with the high frequency range, because depending on the system, the efficiency of the field grading material will depend on the frequency, on the voltage frequency. So it's I think it's a long work to go or still some work to be done to solve the problem of the triple point. There's some French speaking there. So are there other questions here? Okay, there was a question from Jerome asking if we have to ground the shield on both ends. Well, you have answered, Arjen, that it is not necessary for the partial discharge point of view, but of course, EMI and losses in the screen, we may either bond or not at both ends, yeah. Anything else? So sounds like that all of the questions have been covered. If not, just yell out. So then I would say we can switch to the next presentation, which is from Arjen, related to improve models to predict the maximum current that the cable is able to carry.
Okay, thanks. Hopefully you can see that slide.
Yeah.
Okay, thanks all. So while I'm going to speak here and present, a lot of the work that you will see here was done by Thomas's colleagues at Nexans within the kind of FEA modeling teams. Sadly, those colleagues couldn't be here today. So I just agreed to do this part of the presentation. Just by way of background, we know, of course, and the whole driver for this work was to facilitate increased amounts of power being shipped across the airframe. But that would be done potentially using AC cabling, which would be operated at high frequency and would be quite high cross section. So in this bit of the presentation, I'm going to talk about the modeling that was done to try and understand the challenges that would cause. And then Laurent will follow up after this presentation and will showcase the experimental test that was done at IRT in association with this FEA work. We, of course, have guidelines for the ampacity of aircraft wiring at the moment. This is an example from one of the SAE standards. But as with many standards, of course, there's no particular background to how these values were derived. And also, what would be the issue of things like skin effect, proximity effect, if we're working at more than 1 kilohertz? And what may be the impact of insulation thickness increasing on the thermal capacity of cables? So we wanted to make sure we had robust tools to forecast ampacity going forward. The models we developed were in COMSOL. The model accounted for dual heating, so the I squared R losses, which of course in turn had to model the change in resistance as a function of both temperature and skin effect and proximity effect. We looked at, of course, the induced current flow in the screen or the shield. And you'll see from the experimental data that Laurent will talk about, you'll see the importance of the current flow in the shield on the thermal capacity of the cable. Within a pulse width modulated system, of course, you may expect fairly significant levels of harmonics in the current. So while the current might be quite sinusoidal, it will have likely third, fifth harmonic frequencies. And then, of course, finally, you've got to understand heat transfer. So the passage of the heat from the conductor across the insulation and into the air itself. So within the modelling that we had models that certainly worked, and I just want to pick out a few key results here that show you a couple of the things that we learned. First of all, harmonics can be significant, although they're not massively important. If you look at these two cases here, cases A and B. So case A is a pure sine wave. Case B is a much nastier high harmonic content waveform. And even with a fairly high level of harmonics, there was only a small change in the maximum temperature that we saw in these particular cables. So 285 compared with 281. I think you've got to be careful, of course, making the conclusion that harmonics don't give you significant temperature rise. That may vary as a function of conductor cross-section. So as conductors get larger, things like skin effect, proximity effect, and the effect of harmonics will only increase. Another thing that was looked at in some detail was the impact of bends. Compared with cables that you would normally find on a ground-based power system, cables in an aircraft will go through much tighter bends. And we wanted to understand what the impact of those bends could be on the thermal radius. So what you can see in the bottom left is prediction of the losses in a cable as it goes through 3 different bend radiuses. And you can see this as a function of frequency. So of course, we're interested in higher frequencies potentially because we may have an AC system operating at, say, 1 kilohertz, 1.5 kilohertz, 2 kilohertz. But you can see if we go through a tight bend radius, then at those at those kind of frequencies, at the kind of kilohertz level, we can certainly get a 1% increase in our losses in the locality of that bend as a result of the proximity effect influencing the current flow. So it's really important in modeling cable circuits, and this was quite a discussion throughout the project, was you can't just model let's say 3 cables in an isolated manner. You really have to think about modeling the cable as it passes through the airframe to understand where the likely hotspots will be. And of course, that complex 3D FEA modeling is challenging, but absolutely necessary if you want to optimize the cable system. For me in the modeling work, the most surprising result on a personal level was the lack of dependence of insulation thickness on the rating of a cable. So this was actually a model for unscreened cable, but you could equally apply it to a screened cable with a sheath connected at one end. And what you can see here, we have a number of cable sizes, which are the values on the legend, ranging from 4mm to 14.9mm conductor diameter. And as a function of insulation thickness here, you can see increasing from 1mm insulation to maybe 10mm insulation doesn't significantly impact the current flow that can be passed through the cable. If anything, an increased insulation actually gives you a slightly higher current rating. Now, this seems counterintuitive, but this slightly larger insulation thickness actually gives you a bigger cable surface area and aids the heat transfer into the air in this case. So adding insulation certainly doesn't significantly reduce your current rating. And this means there's an interesting question to be made between insulation and cable reliability against the size and the weight of that cable in the aircraft. But certainly, unlike some other cable systems, you wouldn't see a big drop-off in performance as insulation thickness is added. So within the modeling, we've seen skin effect and proximity effect definitely having a significant impact on the rating of the cables. And what this really means is large diameter cables may well not be preferred, because actually if you keep on adding diameter to your conductor, but that conductor is not used as a consequence of the skin effect, then why add it? You're just adding weight for no value. It is important to look at the current rating associated with bends, and these can be more significant at high frequency. And as I've just said, the insulation thickness increase actually delivers a marginal increase in the current rating and not a decrease. There is, though, this big important linkage, as has already been picked up in some of the questions, about the current flowing in the screen of the cable with what that means in temperature rise. And some of that is best demonstrated through experimental test. So I think at this point, I'm going to pass over to Laurent. Laurent will take you through the experimental work in this space. And I guess it's probably best if we pick up questions on thermal aspects at the end of Laurent's presentation, if that's okay. Okay, Laurent.
Okay, thanks. I will share my screen. Do you see my screen?
Yes, thank you.
Yes.
Okay, so just I will talk about what we have done in this project about thermal testing. So we have developed a small test rig to assess the thermal of the cable, and we also try some cables and try investigate some impacts of the harmonics and so on. So just a quick overview of the bench. So you see the electrical architecture in this slide. So at the bottom right, you see the cables that we will test. So the three-phase cable. On one side, we connect the three-phase to a voltage inverter, and on the other side, we connect together the three connectors. We short-circuit them by a bus bar. The inverter is driven by our proper control laws. So we develop our control laws, so our regulation and our PWM strategy in an Opal-RT platform that can drive the inverter driver and impose the current we want in the conductor. We have after that use a classical acquisition system to get all the sensor, and we all drive this by a computer. Now, some component of the bench. So first one, the inverter. So at the beginning of the project, we broke the inverter several times because it's quite a specific usage. We don't have any load. There is no electric motors and so on, and we are very low power factor usage in this case because we switch a lot of reactive power between the DC capacitor and the inductance of the cable. So we broke several times the DC capacitor on the inverter, and we have to design, to specify, and to purchase a dedicated and tailor-made inverter design. So you see the characteristics on the slide with a huge oversized DC capacitor and the capacity to go up to 3 kHz to investigate the fundamental frequency. On the bottom left, you see the control law. So we developed them in MATLAB Simulink, the current regulation and PWM generations, and we use compiled code executed in Opal-RT platform. On picture on the bottom right, you see an enclosure. I will come back to this enclosure later. This enclosure is important because we can control the ambient temperature with that enclosure. It means that we should take care of not be sensitive of the airflow in the room. For example, air conditioning airflow is a parasitic airflow. So with this enclosure, we can master and control the ambient temperature of the cable. And finally, we develop an HMI to supervise or synchronize everything on the bench. If we look inside the enclosure, so we integrate the cable. So on one side, we connect the three-phase cable to the inverter. On this side, I think you see my mouse. We take the EMC braid, the EMC shield together to connect themselves at one point. And on the other side of the cable, we put together the short circuit of the conductor, but also we take the three EMC shield and EMC braid that we connect together, of course not connected with the two parts. On the picture on the bottom, you see the thermal installation. So a lot of sensor used on the surface of the cable, but also we put some sensor inside the conductor. So just a quick video in order you can see the actual size of the bench. So in this video, you will see the integration of the cable. So the three-phase cable are hung at several points of the enclosure, and we can pilot drive this inverter dedicatedly. So it's a 6-meter length enclosure. It's necessary to have sufficient length to be homogeneous in the temperature distribution. I will show you a first test we have done. In this first test, we try to put a sinusoidal set point. So we want that in the three-phase there is a sinusoidal current, and we set up a high fundamental frequency on 1.5 kilohertz. And if you look at the plot on the left, we got a quite good sinusoidal current, so not a lot of harmonics, except from the PWM harmonics, but it's normal, it's a voltage inverter, and it's well balanced. What is interesting is to look at the plot on the right. So it's the current circulating in the braids in the EMC shield, and we have free current circulating in this shield. It's an end-use current. It is not a regulated current. It's end-use because there is a capacitive coupling between the conductor and the shield. And you can notice that the value of the end-use current is not negligible. For example, we impose 230 ampere in the conductor, but we got 50 ampere in the shield, and these end-use current are quite well balanced. It's like if it's a new three-phase end-use system, because if we sum all the three current, we are quite equal to zero. So well balanced and current in this system. So now, if we look at the thermal evolution, in this slide you see the thermal test. So first of all, we need a long time duration to wait for a steady state temperature, so more than 1 hour. And first of all, if you look at the top graph, you can see the regulation. So with our inverter, we keep during all the tests the same value of the current. So it's a sense current, a recording current, and it's important to check that because of course there is an evolution of the resistivity with the temperature. And we need to have a permanent regulation to keep the same current in the conductor. What is interesting also is in the dash plot, you see the current end-use in the EMC braid, in the shield, and it's quite also constant and well balanced between the three shield. When we wait for a steady state temperature, we can see on the plot on the right a cut in which we represent all the sensor used with one sensor in the middle of a conductor and other on the surface. And you can see the color of the square is linked to the temperature, and you see the color bar on the right. But as expected, the maximum temperature is in the middle of the top conductor, and the lower temperature, except for ambient, is on the surface on the bottom. And you see in this graph that the blue one is the higher temperature of 186 degrees C in this test, and the red and the green curves are the maximum and minimum temperature on the surface of the three-fold configuration. So you can see there is quite strong gradient between the maximum temperature in the conductor and the minimal temperature. Then we have a second test. In this test, we try something that by the control laws we add harmonic 3 signals, and as you can see on the plot on the left, the waveforms of the signals is quite distorted. So there is a strong harmonic 3 end-use. So we set up as the harmonic 3 must be half of the fundamental. And what is interesting is that the end-use current in the shield is not the same waveform than before. And due to higher frequency of the harmonics, the end-use harmonic 3 is higher or quite the same than the fundamental end-use harmonics. So it's quite interesting. It means that depending on the harmonics content in the conductor, we don't not get the same end-use currents in the braid. And in this case, we got more end-use current because instead of 50 ampere, we got now 66 ampere. And that's why we have more losses in the braid, and so outer cable in this configuration. So this slide is quite the same than what I presented before. So I will not explain all this slide, but just everything is like we shift a little bit, we increase all the temperature, and now we have a temperature of 211 degrees C. Just to compare, I make a slide with both results. So on the left, only a sinusoidal waveform. On the right, with the harmonic 3 waveform. And what I didn't explain very well, but by our control, we also regulate to have the same true RMS current in the two tests. It means that in this test or this test, what is circulating in the conductor is the same true RMS current, and we expect the same losses in the conductor. But there is not the same end-use current in the shield, as you can see the value 50 or 66 ampere. And so the impact is important on the temperature distribution, and in configuration with more harmonics, there is warm, hotter temperature. It means that we have an ampacity decrease if we have a signal with a lot of harmonics. Okay, so now it's my last slide for today. This slide can make the link with what Ian presented before. It's about comparison between the experimental and the simulations. And first, at the beginning, we compare with only a sinusoidal set point. So in this case, we see that deviation is quite low. We are good results. When we turn on harmonic 3, it's quite interesting also. We have a little bit more deviation, but it's difficult to well understand. And our assumption now today is maybe there is an important impact of the contact resistance. In fact, it's not easy to how to say that to connect the ground and to contact all AMC braid. And as it is an end-use loop, the additional resistance have an impact on the end-use current. So could be one way to explain why there is more deviation when we put on harmonic 3. Last thing interesting to notice is that when we shut down the power, you can see in the cooling phase that the both experimental and modelization are quite well fit, and there is more deviation. So that's all for my presentation. So thanks, and maybe I will stop my sharing to see if there is some question.
I think, Laurent, just while people think if they've got any questions, there's been some interesting conversations going on in chat as well while you speak. I was just flagging one thing. Jerome asked about obviously, or flagged that the current in the shield, as you've shown in your measurements, can reduce ampacity because it increases temperature. In the conventional power system, of course, you'd get over that by bundling your 3 cables together into one collective shield. But in the context of an aircraft, I guess that will give big issues in terms of installation flexibility going around corners. So it's probably a balance between ease of installation versus getting slightly more current through your cable. So I don't know, do we have any more, or are we going to wander on to the next presentation? You saying something, Thomas? You see your.
Yeah, I think, yeah, I was muted. I think we can go to the next presentation.
Okay, it's Gilbert now.
Okay. You can listen. You can see my slides.
Yes, we can.
Okay. So I'm Gilbert Tesset from CNRS and from Laplace Laboratory in Toulouse, and this part concerns the aging assessment of materials and cables and cables. So I will present first the hypothesis and the limits in which we have done the aging, the work on aging. First, I will come back quickly on the backgrounds on materials of interest that were used in the project under thermal and electrical stress. I will present also a kinetic model that we have used for addressing thermal degradation aspects. I will show also the test rigs that we implemented for the thermal aging assessment, and some results of ongoing work that we can produce. So first on the hypotheses and objectives. So we want to anticipate risk of a system evolution based on the operating electrical and thermal stresses. We have worked assuming a partial discharge-free situation in the initial state, because all what concerns PD occurrence was used as a criteria for the design rules, initial design rules. Within the time frame of the project, we couldn't make lifetime estimation. So what we did is that we considered the computed stresses on one end and available data on materials that we can find. We provided some arguments that aging cannot occur in the design stress that we fixed, and also we assessed from the thermal aspects the things by experiments. So the materials that we investigated, as Thomas said, polyamide, PTFE, and PFA to be used as extruded insulation. And we can see aging on two aspects. First, on the evolution of material integrity, like oxidation, transition, etc. And the other aspect is on system integrity loss. If you have delamination, shrinkage, you can produce a PD when initially you didn't have any. So the test will be achieved regarding these two aspects. So regarding the background on materials, there is extensive literature considering polyamide. For example, there's a review paper here by Sombeliam on the breakdown aspects of polyamide. And what we know from the literature is that if we, especially we were interested in the high temperature withstanding, and whichever the condition that were used, there was no breakdown field under 80 kilovolt per millimeter for temperature up to 200 degrees. There's an example here of breakdown field as a function of temperature, where we are beyond 200 kilovolt per millimeters up to 200 degrees. And if we consider the frequency, which is an important aspect for the project, of course, there is no special degradation of the breakdown field with increasing the frequency, and even an increase of the field apparently that could be due to the fact that we have perhaps less losses when increasing frequency. If you look at, there was also in this field recent papers by 100 people working in the field of aircraft rise, where they developed for polyamide and also for some fluorinated polymers, Daikin-based kinetic model for aging. So it was applied mainly for thermal degradation, but also there was some initiated work regarding the electrothermal aging. So, for example, there was a work with where they tested the breakdown field after thermal aging with and plotted it as a function of the weight loss of the materials. So there was a loss in a breakdown voltage from 17 to 11 kV, but it just was for over 20% weight loss. So there was even if there was a significant degradation, at least in terms of weight loss, still the material could withstand the field. And if we look at the fields, the drop in intrinsic breakdown field was only by 10%. So even with a significant aging, there could be still material that were capable of withstanding the field. If we look at the similar things for PTFE, there is also work on breakdown field achieved after thermal aging up to 200 or even 400 degrees C. So here 250, 300, 240 degrees C, the breakdown field as a function of aging time. And we can see that for this material, there could be apparently even an improvement of the breakdown field with the aging, and there was also either no evolution considering the infrared spectroscopy, for example. So it seems that the materials can really withstand the temperature that we are working with, at least these two kind of materials. What we
Sounds like we have lost Gilbert.
You can see me?
We can see you, but we haven't heard you since 1 minute.
You can see me here, the slides?
It's good, now it's good. Go ahead.
Okay. Okay, so I start with, that's okay for the PTFE? That slide was okay?
Yeah, that was okay.
Okay. So yes, on the Daikin-based kinetic model for degradation. So our goal was to use the kinetic data of for degradation that were achieved with the ramp-up experiments with the thermogravimetric analysis in order to forecast how fast the material could lose weight as a function of time. So it's a multi-parametric model. The kinetic is a bit complicated. We use essentially data which were fitted to the ramp experiments. So what was done, for example, here is for the case of PTFE, starting with data on the TGA analysis, which were recorded as a function of heating rate. So we have different heating rate. The higher the heating rate, the higher the apparent activation, the apparent degradation temperature. So we can extract activation energies like that from these curves. And from this data, we can convert into weight loss as a function of aging time. And so, for example, we could select a criterion for aging of with 5% loss, and we can compare different materials in this way. So that was done for PTFE. We can see that at 250 degrees, we have lifetime beyond 100,000 hours here. And with this data, so we used data from the literature for PTFE and polyimide, and we performed our own TGA measurement that was done by Nexsense on the PFA material because there were no literature data on that. And here there is a comparison of the weight loss as a function of temperature. That's something predicted by the model, comparing PI, PTFE, and PFA. And from these results, so that of course that has to be checked by experiments, but according to this result, PFA would have a better thermal withstanding than the other two materials. And that is due to an apparent higher activation energy for the degradation. That will be presented in the next weeks to the ICPDM conference. So, if I wrap up the work on the thermal modeling, of course we can question the validity of extrapolating degradation curves achieved in a relatively short time to low temperature. We can have different processes at lower temperature. For example, maybe oxygen diffusion can be something important. That is a first approach. The second point is that we have high breakdown field for PI and PTFE for temperature of 200 degrees C and more. PFA is claimed to have similar withstanding under field compared to PTFE, according to the providers. We use a relatively safe design field of 15 kilovolt per millimeter for designing the cable, so we are far from these limits. And we believe there is no real risk of failure due to the intrinsic material evolution, supposing that we have no PD into the materials. So that was for the theoretical aspects. So now we go to the experiments. So we have built two thermal test benches for continuous thermal aging at 260 degrees and run in parallel two aging on two cables for months. And during this time, we recorded periodically PD inception voltage and patterns, the DC current, typically once every week or 2 weeks. And we also made sampling, take samples for physical chemical measurements. So we have a first full set of measurements on taped PTFE, shielded or with unshielded or unshielded cables, and there's a second one which is underway with the PFA cables produced within IVACS. So that is the test bench that we have used. So we have different arrangement for shielded and unshielded cable due to the way that for detecting for collecting current or detecting PD. For the shielded cables, we treated just the end of the shield here to try to avoid the discharge at the end. So we have one end inside the oven and the other one outside the oven, and we collect current, DC current through the ground here outside for the DC current measurements. And for the unshielded cable, we designed we machined ground plates in order to have that which are shown here, in order to have a distribution of distance between the cable and the surface, in order to have to explore different distance for the PD occurrence. And also the plate serves as connecting terminal for the DC current. So that was done that was two PTFE insulated cables with 2.7 millimeter thick insulation. So regarding conductivity measurements, we did it with 3 kilovolts applied to the cables, and here are the results for the current as a function of aging time. So that was all measurements were achieved at 260 degrees PD or DC current measurements, and we can see here that we have a slight increase of the current by a factor grossly of 2 or even less than 2, and we don't have a significant difference between when comparing a shielded cable and unshielded cables. So that's quite reproducible results, and we still have a very low conductivity even after 4 months of aging. If we switch to the PD measurements, that's the results obtained for inception voltage in red and extension voltage in blue here as a function of time for the shielded cable. We have inception voltage which are above 2,700 volts, and there is no significant evolution as a function of time. That's one point. Second point is that compared to unshielded cable, we have a relatively low PD-EV, and we suspect that there was a limit here in the fact that probably the discharge were occurring at the termination of the cables. In case of unshielded cable, we have a much higher inception voltage, beyond 4,000 volts. We have a drop at the beginning, which is noticeable. It was inception voltage were at about 5,500 volts. It decreased to about 4,500, and then it tends to stabilize. And even the last point here didn't show any more a decrease. So that seems to be quite stable. The measurements consisted in infrared emissivity. Infrared emissivity is important for the thermal modeling. The coefficient of emissivity enters into the thermal modeling of the cables, and we could see that we have a clear difference depending on shielded and unshielded cables for the coefficient. That seems to be probably linked to the thickness of the outer Teflon layer of the cable. But except for the difference that are due to the construction, there is no evolution as a function of aging time. An important aspect is also the TGA experiment. So we did a TGA after aging at different times, and again, there's absolutely nothing detectable a difference between the different materials. That's a proof that the materials can withstand the temperature. So a wrap up about these experiments. We didn't detect any change in the PD activity in a shielded cable, and we believe that probably we are testing mostly the shield ends of the cables in this condition. For the unshielded cables, there was a decrease in the inception voltage, detectable decrease, and before stabilization. And for the current measurements, it was relatively stable over 3 months. We had a detectable increase in conductivity, but still it's very, very low conductivity for the materials. For the extitude test, there was no either any sign of evolution of the PTFE material. And so we are now currently repeating all these series of tests with two cables with a PFA insulation. That's something started 1 month and a half ago, and we still have all the July and probably after July to complete this test. So I finished with the presentation.
Okay, so I will now share my screen.
Just want to check there's no other questions for Gilbert first, Robert.
Sure.
I don't know, Thomas, is it worth Gilbert just answering that space charge one a bit more, or are you happy?
Sorry, tell me. The question of Chris.
No, there was a question from Alain Philippe that Thomas has already answered, but I don't know if you've got anything to add. So Alain was asking, at what field level do you think space charge effects can be neglected on an installation?
That's something out of IVAC's stuff. I think space charge is. I think that I'm not convinced we have big issues of space charge regarding internal field internal to the insulation as regards the aerospace stuff. The point is that if we charge surface, maybe we can have impact on the outer discharge on discharge into the ambient air. If we charge material, you can modify the field mostly into the air around and change the discharge there. But for the internal stuff, I would say, well, that's something that we check, but I would say maybe it's not the main issues there.
Was one of the questions from Chris? Yes. Can you see it? So normally
the constraints that could be done post aging. But we don't. Yeah, we are not in a plan to to make a breakdown test, because making breakdown test means that we need a reasonable amount of samples and so on. So it's out of the resource of the project to make breakdown test here. It was not our plan, I think.
Okay, so I think there are no further questions here. So then, yes, Robert.
Can you see my
start?
Can you see my slides? Okay.
Yeah, all good.
Good. Okay, so I'm going to be talking a little bit about the challenges that exist in getting partial discharge measurements to be consistent and reliable. And I prepared this presentation with help from Gilbert, and this has been extensively presented at conferences in the past. So, oops, again. So what I'm going to talk about today is that increasing voltage levels are going to increase the risk of partial discharge quite considerably, especially relative to ground-based applications and in the low-pressure environments that we find in aircraft. So what we need is a robust suite of test methods to validate any designs that we propose. And there are a number of test methods already available, notably ASTM D3032 and the BSEN standard. But we don't know whether there are any differences between those test methods. So what we did is to perform a round robin of measurements of partial discharge inception voltage measurements to try and identify differences and variation between labs as well. So in brief, there are three distinct test methods for partial discharge as described by the standards I mentioned. The first one is the flat plate method. This is really simple and straightforward. You secure your test piece to a flat metallic grounded plane, bend the wire up into a U shape, and then connect the HV input to the exposed wire. We then have the mandrel test, where we make 10 turns of the wire around a grounded metallic tube. The standard specifies that the diameter of the tube should be 10 times that of, sorry, the radius of the tube should be 10 times that of the diameter of the wire. And then finally, we've got the braids method, which you make a loop of wire, which if I get my terminology correct here, the radius is 4 times the diameter of the wire. There's no specification on the number of loops to make, but the standard does say that you should use at least 850 millimeters of wire, of which 750 of those millimeters are covered by braids. So in the round robin, the 4 different labs in the consortium participated in the testing. These are the details of the different test methods. I'm not going to go through this in any sort of great detail at the moment, only to say that there is differences in the different equipment that was used. So these are the PDIV and PDV results for the wire that we tested. As mentioned before, one of the wires that has been used extensively in this project is an AWG12 conductor, and insulated with around 0.42 millimeters of PFA insulation. All of these tests were conducted at the atmospheric at sea level in the laboratory. And what we see is for the Mandrel method, we get around about 1650 to 2000 volts RMS for the PDIV. For the plate, it's a little higher, around about 1800 to 2100 volts RMS. The most notable difference is that the braid method gives considerably lower PDIV results than the other two methods. The PDEV results follow the same trend as the PDIV results. These are the standard deviations in the results between each of the labs. The lab with the smallest dispersion is Lab C. Lab D had the largest dispersion of results, including the biggest difference between the PDIV and the PDEV values for each of the labs that participated. And the most likely explanation for this observation is that Lab D performed their measurements in a room that was screened from ambient sources of electrical noise. So the chances are that that lab was able to detect much lower levels of discharge than the other laboratories were. So in the second part of this, we try to understand some of the origins of the differences. We did this using finite element analysis. 2D representations were used for each of the test methods. So we've got in the top left picture here is the braid method. A small air gap of 0.5 millimeters was used between the braid and the outer surface of the insulation, or else the braid wouldn't be able to be installed. The flat plate is just a single wire on the grounded metallic surface. And then for the mandrel, this was modelled as 10 turns of the wire. So in terms of the modelling methodology, one of the key ways to predict the PDIV is through the streamer inception criteria. This involves integrating the effective ionization coefficient along the electric field contour lines in electrostatic simulations. The effective ionization coefficient effectively gives you an idea of the number of free electrons that are available, and it's sometimes abbreviated to this constant K. And what we aim to achieve is a K value of 6 before partial discharge occurs. And this is something that's been reported in the literature for wires and cables of this particular size. The effective ionization coefficient depends both on field and pressure. So what people do is to take measurements of this quantity, and then what they do is fit the data to come up with functions like this one. And this can be used to in the simulations to simplify calculations. So one of the labs had a slightly different test setup for the flat plate. So the geometry was considered in the models in this case. For the other labs, we estimate that the PDIV for the flat plate method is 1870 volts RMS. but with this specialized test setup, there's also the possibility of small air gaps. Now, we don't know exactly what the size of those air gaps is, so it's very difficult to make an exact estimation of the PDIV. So looking at the sort of sensitivity we see if we have a 0.1 millimeter gap, we get 2040 volts RMS, and then it falls considerably as that gap gets bigger. So the next is to look at the Mandrel method. This method also has a predicted PDIV of 1890 volts RMS, so a very small difference compared to the flat plate. So it might be that the slight differences seen between the labs and the two test methods are really down to things like if there's any air gaps between the mandrel and the wire, or spacings between the wires, and also the noise levels and the detection systems that are used. So finally, onto the braid method. As I said before, 0.5 millimeter gap. You can have different amounts of displacements between the axis of the wire and the braid. So studied this and looked at the variation in the PDIV. So when there's no variation and you've got a perfectly uniform field, you have an estimated PDIV of 1550 volts RMS, and this falls to 1410 volts RMS when you've got a displacement of 0.4 millimeters. And you know, some of the differences in the PDIV values are obviously attributed to field uniformity, but also when you compare the braid method to the flat plate and mandrel methods, you've also got to consider that you've got lots of very small diameter strands that could potentially enhance the electric field around the in the proximity of the braid. Okay, so just to sum up, we've done the round robin. We found that there's variations between methods and labs, and we've proposed a whole series of different explanations for why these differences might occur. Oops. So are there any questions whilst I just swap over slides?
Well, Robert, on the chat, there are no questions.
I think there was one that's just a typo that I saw in my peripheral vision, that Patrick said it was 307 instead of 347 for the standard. Is that correct?
Yes, just a mismatch error, typing
Yes.
error, Robert.
Yes, I think that's just a small error in my typing.
So there's a question from Jasper. He's asking, what is the impact of the tightness of the wire around the mandrel?
So this is something that we've not sort of formally tested within the laboratory, but from a purely clearance point of view, you would expect some increase in the PDIV because you've got that extra bit of insulation from the air in the clearance between the wire and the mandrel.
Okay. So, thank you. Okay, so seems like the answer was sufficient for Jasper. So if there are no further questions, there's one from Guillaume.
Sorry, I just missed Guillaume's question there.
Just popped up. So he's asking if you compared the simulations with experiments.
Yes, we'll come to that in this presentation.
Okay. And another question is if we will make the slide pack available to the attendees. I think the answer is yes. There's a question from Daniel. He's asking if the Mandrel test method is the most conservative. I think we can say, based on the results, that is the braid method is the most conservative.
Yes, I would say, you know, it's definitely the braid that gives the lowest results across all of the labs. So definitely I think the other thing that needs to be considered as well is whether you're sort of comparing like with like, because this is an unscreened cable initially in terms of EMC screen, and you know we installed the screen over the braid over the top simply for the purpose of the test. So it depends what configuration that wire is used in the real application and not just during the test.
Yeah. And then there's also a question if we have investigated the impact of the wire lengths on the PDIV results.
I would say that's something ongoing. I think there may be some dependence, at least theoretically. You've got more potential locations for defects and a larger surface contact area for all three of the methods, providing that you know you apply the whole length of the wire in the test.
And there's another question. A lot of questions now. There's a question from Jerome who says that the EN standards forbids the use of sharp crimping devices like a crocodile plier. Do you think that it has an impact if we use crocodile clamps?
I think there was some differences between each of the labs for the in terms of the use of different terminations used in the tests, but I mean the results that I know about used crocodile clips, and I don't think there's a serious impact on at least on the PDIV, maybe on the spread of the different results, but so far I don't think there's much in the way to suggest that the termination makes much of a difference.
Okay. There's another question asking if we investigate the bend radius on the PDIV, but we haven't made any investigation on that. We just use the bend radii as they are specified in the ASTM standard, as you mentioned. So 10. The bend radius for the Mandrel method is 10 times the cable OD, and in the EN or the pulled on braid method, it is 4 times the cable OD.
Yeah, and I've just commented there, Thomas, just, you know, reflecting back to one of the previous questions, is the Mandrel method most conservative? Of course, the Mandrel method is just impractical when you're doing those fat cables, you know, just because it's just, well, you just can't do it in a sensible test chamber in a lab. I'm just conscious of time, Thomas. We've got 15 minutes. Do we need to?
Okay, so we need to speed up. Yeah.
Okay, so I'll move on to the next presentation. So this is about predicting PDIV values and also power density. There have already been discussions about the potential benefits of screened cables, so I'm not going to discuss that anymore here. But what we do need to do is to try and quantify the benefits that screen cables might give when compared to unscreened designs, and can we use metrics such as the gravimetric or volumetric power density. In terms of contents, I'm going to talk about how we estimate PDIV in unscreened and screened cables. And
I don't think we're seeing your slides, Robert. Sorry.
Yeah, still on the.
You might need to just stop your share and start again. Sometimes it doesn't like it if you change presentation.
Sorry, my apologies. Okay, so we've got use of screen cable. It's the first slide, yeah?
Yeah.
Okay, so just in terms of the contents, I'll talk about the different methods that are available for PDIV forecasting in both unscreened and screened cables, and then we'll try and integrate with some thermal modeling that Ian presented earlier. So for unscreened, Thomas has already talked about Halleck's method, so I won't go into too much detail. All I'll say is this is the equation for the method, and it takes into account the thickness of the dielectrics and the permittivity of the electrical insulation. And it basically involves estimating the percentage of the voltage in the air gap between two wires, and then comparing the amount of voltage with the breakdown values that have been measured by people such as Schumann and others. So very quickly, here are a series of different PDIV predictions made by Halleck's method, and some experimental results that have been measured in different laboratories, and we see a very good agreement between the two, so we can be confident in those results. Stream inception criteria, I've already been through this in the previous presentation, but very quickly you can see here that in the image we've got the electric field contour lines, and we evaluate this equation along these lines until we get a value of 6 for the variable K, and this is our partial discharge inception voltage. So one of the previous questions was to do with, have we validated these models with experiments? The answer is yes. So this was the AWG 12 wire again with the same thickness of insulation. Simulations were run in COMSOL using electrostatics and the charge particle interfaces. Pressure was assumed to be 238 millibars, equivalent to around about 30,000 feet. We were trying to simulate the sort of insulation thicknesses and PDIVs we might need if we had a sudden loss of pressure at high altitude. So at this particular pressure, the estimated PDIV is 1.06 kV RMS, and these are in the table are the PDI-V values as measured using the flat plate methods from the previous presentation. Again at 238 millibars, and you can see that we've got a very good agreement between the models and the experimental results. So onto screened cables. We looked at the maximum operating voltage as a function of conductor size and insulation thickness. In this particular case, we assumed that there are no voids within the insulation, so the only factor affecting the operating voltage will be the breakdown voltage of the PFA insulation. And again, as with previous presentations, we're using 15 kV per millimeter and then using equations to calculate the maximum operating voltage. And you can see from the graph that we're getting sort of 20 kV up to 100 kV for the operating voltage, and these are voltages that are clearly not going to be seen for a very long time, if at all, on aircraft. So we then considered that the operating voltage might be limited by something else, and something else in this case could either be a void within the insulation, or indeed it could be the termination of the cable and the issues that we've already discussed around the screen cut. So there's an equation that gives the inception fields for a gas-filled void, and in this equation A, B and N are constants, and these depend on the gas and the void diameter, and then we've also got pressure and void diameter in the equation as well. I'd like to say that there are two very important assumptions that this analysis makes. The first is that the void is filled with air. However, there is a very fair chance that the gas inside the void may not be just pure air. So there are things like gases that may be trapped inside the void during manufacturing or evolved due to thermal aging that may change the values of these constants. The second important assumption is that if you're trying to evaluate a worst case scenario, such as 238 millibars, then you've got to assume that the gas pressure inside the void is the same as the air that surrounds the cable. And it's not currently well understood how long it will take for that equilibrium to be reached. So in this table, there are a lot of results here. It shows the maximum void sizes that you can tolerate within the insulation for a particular operating voltage at two pressures. The top table is sea level 1000 millibars, and then the bottom table is 238 millibars again. In the table, there's some results that says no PD, and what this means is that the void size required for PD is bigger than the insulation thickness. So effectively, you would have no insulation between the conductor or the conductor screen and the insulation screen. So effectively there you would be looking at a full breakdown in the air gap. So this is therefore a different phenomena altogether. Insulation thickness and the pressure both have an impact on the void size that you can tolerate, depending on the voltage as well. So on to some implications for power density. Very simple analysis. We use the PDIV values obtained for unscreened cables, and the current ampacity levels estimated for a maximum operating temperature of 200 degrees C, and calculated the power, and then used the density to estimate the mass of the cable per meter to give sort of indication of the gravimetric power density in kVA per kilogram. And as we've discussed in previous presentations today, there's a clear peak in the power density whereby you stop getting any benefit in terms of increasing current or increasing safe operating voltage, and then the mass sort of starts to cancel out the benefit, and also there's the possibility of the skin effect, increasing the resistance of the conductor as well. So I think we've discussed this in fair detail before. So basically, in summary, we've developed a series of validated models to forecast PDIV, safe operating voltage of screen cables. The chances are it's going to be limited by voids in the insulation or surface surface discharges in in proximity to the screen's cut, and then unscreened cables, we've seen that the maximum power density can be limited by the additional mass and resistance of the cable from frequency increases, and then the power density of screened cables is likely to be much higher, but this may be limited by the presence of internal voids or indeed discharges at the screen cut. So that ends my presentation. I'm happy to discuss questions.
There was one question, Robert, that came in just about the particle tracing method and kind of where that came from. But I think I've found the web link that we probably found when we were looking literature about this, and I've just pasted that in a link. I don't know, Thomas, did you want to pick up that AS50881 one anymore?
I didn't get that.
Sure. Oh, Thomas is on mute.
Yeah, I'm on mute. Yeah, I didn't compare both methods in detail, to be honest. I'm just looking here quickly for one. I just compared measurements with the Halex method, as has also been presented by Robert, but I did not verify them with the curves given in the AS standard.
And I think, Manu, it's something I've complained about before, but I've never actually done anything about. Is I already think there's the need, even if you believe the curves in AS50881, and I've no reason not to, is how do you apply them to phase to earth versus phase to phase, and what do you do about pulse width modulation? So that's one of the things that we did talk about, and I think we all agreed within the group. Better guidance on how to use and implement those in new systems would be really worthwhile.
There is another question from Manu related to the ambient temperature and the impact of the air density.
Let me pick that one up. Manu, you're absolutely correct. You know, the temperature needs to be considered in terms of the ionization coefficient, and we'd normally do that just by doing an equivalent reduction in pressure. So I always think, you know, the E upon P type relationship really needs to be almost E upon relative air density would be a better way of phrasing it sometimes. Thomas, Laurent, is one of you two going to wrap up? I guess there's people asking about, will we make the slide? How are we going to make the slides and recording available?
I think yeah, the slides will be made available. The recording will also be made available. I think they will be made available on the website of IRT.
We had to define the way, but of course we will find a way to make this available.
And we'll send the link out, I guess. We'll send the link out by email to people on the call.
Yeah, we will send the link. I have copied the list of attendees, so we will send them the link where you can download the presentation and the webinar, the recorded webinar. Oops. So a lot of so sounds like people have been impressed by the work we have presented. So thank you to all for your wishes, your best wishes there. Yeah, and if in future after the webinar you still have questions, you know our email addresses, so you can contact us, and we will try to answer those questions then to you. Laurent, do you want to add anything?
No, I thank you all of us, for all of you, for participating to this webinar. I think it's an interesting webinar. We present some results of the projects, and I have nothing to say more to conclude this webinar.
Okay. Well, thank you all to you for the participation, the interesting discussions we had, and hopefully talk to you in the future. Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.